Okay, so I'm Steve Croft, and it's a pleasure here to have Maryna Viazovska, who is winner of the New Horizons Math Prize, and wanted to talk to you about how you first got interested in math, and when did you develop a passion for mathematics?
So I grew up in Kiev in Ukraine, and somehow even at school mathematics was always my favorite subject. So when the time came to choose somehow my specialty at the university, I did not have much doubts about choosing mathematics.
Do you think there was something in particular that kind of grabbed you about math at an early age?
Yeah, so like one thing I really liked about math, it's somehow in math you always know like where is truth and what is right and what is wrong, and where the truth is. And it's not always the case about all the other subjects.
And how do you figure that out when you've actually kind of got the correct answer? Path.
Yeah, but I mean, like in general in math, because in math, I don't know, somehow, yeah, you have in math you have axioms and proofs and then theorems, and a theorem is always either wrong or right. And I know, for example, if you're doing an exam in history and somebody asks you, so what were the reasons for French Revolution? How can you know which answer is wrong and which is right? So this was always very mysterious for me, and maybe that's why I never liked history and liked mathematics.
But is part of math trying to figure out maybe what another mathematician has done wrong and try and do it right?
I don't know. I thought, this may be a beautiful part in mathematics, that it happens very rarely that mathematician does something wrong and he cannot find it by himself, but somebody else. So there are a few cases like this in history, but they are rather rare.
So what excites you about your area of math?
My area of math is number theory, and maybe one thing I find most interesting about number theory that it's very easy to ask different questions there, and still very difficult to find answers to them.
And I understand that there are applications in geometry in particular regarding packing of spheres. Can you tell us a little bit about that?
I cannot say it's an application in geometry. I think this is just one of like basic geometric questions. So this is one of those very natural questions. So you have a ball, and how many balls you can put in a very big box. And so this answer was asked in 17th century, or maybe even before, but from 17th century it became known as Kepler conjecture. And for example, in our three-dimensional space where we all live, it was solved only at the end of 20th century. And also it was somehow very difficult proof with a serious use of computers. And so what I did, my work is about bigger dimensions. So here maybe like most mysterious part is like what maybe not so much people know is what are the bigger dimensions and what are they good for. So I solved this problem in dimensions 8 and 24. So it turns out that actually in dimensions 8 and 24, the solution is much easier than in our common dimension 3.
And so it's difficult to explain mathematical research to somebody who doesn't really understand math, but how hard is it to explain your work to a mathematician from a different field?
I think the formulation of a problem is not that difficult. So I think this is something I even try to explain to high school students who of course, who study geometry. Then they even study the vector spaces, and they understand what higher dimensional space is, and then there is no conceptual difficulty to explain at least the question to them. What could be a bit more difficult is to explain the proof.
So how would you explain to a high school student your work?
Yes, I would explain them that if you consider eight-dimensional space, so it means that we have every point it would have 8 coordinates. So for example, in our space, every point has 3 coordinates. It would be somehow how much you have to go like north or east, north or south, or west or east, and then also how high you are over the floor. And then you know the exact position of your point. But in 8-dimensional space, you would need five more numbers to know the exact position of your point. And then you are still, what is also important, that you are able to measure distance between points. And if you're able to measure distances, then you know what a ball is. So the ball with center at some point, it would be just all the set of all points which are somehow, for example, at distance 1 or smaller to this point. So this would be a ball. And now what we try to do, we try to put as many of those balls into, for example, a very, very big cube in a-dimensional space. And so what we would like to do, which portion of a volume we will be able to cover.
And are there physical implications for this work, or does it sort of exist in abstract terms only?
I don't know, so maybe it's better to ask it to a physicist, so I'm sure that some applications would be. On the other hand, I don't think there is some like very naive application of this result, because I know that a-dimensional space, it appears in some physical theories. On the other hand, it's not a Euclidean space, and there are somehow, like, not all the directions are the same. And also, like, other thing is that maybe what would have applications, maybe the methods we developed to prove this. Because the configuration itself was already known, and people had really a lot of faith that this is the best one, and that we cannot make better. So what new things we have done, we have developed new methods for proving this. And maybe those could be useful, not only for this packing problem, but in some wider context.
Mm-hmm. So how hard was it to make your breakthrough with sphere packing?
So somehow it turned out that it was easier than I expected. Mm-hmm. And
how long did it take?
Just maybe sort of like 2 years, maybe a bit more. So I already knew about this problem for some time, and but then maybe the last 2 years when I worked in Berlin. So this was one of the problems in my research proposal. So this was the time when I really concentrated on this problem, and somehow, in the middle of my research, some unexpected idea came, which I did not know that things work like this, and magically everything worked out.
So there was sort of an aha moment.
Yeah. There was somehow very like short period of time when I actually realized that things will work out.
And what does that feel like when you kind of have that key that fits in the lock?
Yes, it is very exciting, but then of course you still have to like make all the smaller details work. So it was exciting because I understood that it would work, but then still there is this like voice, okay, so but you don't have it written yet, or you don't have it finished yet, so everything might fall apart at the last moment. Mm. But luckily for me, it did not fall apart. So.
Great. Who's your biggest mathematical hero and why?
I don't know. There are many of them. And, I think during the history there have been many like really amazing mathematicians. So maybe my heroes are people who were able to change mathematics or change our way we think about mathematics. Maybe, I don't know, one of my heroes is probably Euclidus, somehow wrote this first book on geometry, and of course we know very little about this person, and because he lived so long time ago. But I think he's certainly one of the person who influenced mathematics for like thousands and thousands of years later. And there are also another, I think, also an extraordinary person is, for example, Henri Poincaré. So. And I don't know, maybe people who revolutionized, for example, mathematics already like, afterward in the 60s, people who developed algebraic geometry and all these new kinds to look at mathematics. Mm-hmm. And maybe there are also much more people. Just
sort of everybody building on everyone else's work.